Okay, let's get started. So today we're going to be a little different. Instead of me and David teaching, we're inviting one of our graduate students, Adrian, who's going to give the lecture. But before Adrian actually gives the lecture, I just want to say a couple of things about your project. As you're probably aware, there's a mid-semester report for your project coming up, and that means you're supposed to have done something by then, rather than just have good intentions. I know you all have good intentions, okay? So just a reminder about this. We moved the time for it. Currently the website says that it's due the Thursday before, but we're going to move it to the Tuesday afterwards. So that's still before mid-semester and before the mid-semester exam. We'd like to know about your architecture for your question answering system. We'd like to know about your pipeline. We'd like to know about the tools you're going to use to be able to do that. We want to break down your responsibilities from within your team. And let's say something about your team. If you've already lost some members of your team, please let us know. Now's the time we can fix it. Okay, you really do want to have 4, 3's probably okay, 2's probably too small. Let us know and we'll reassign the teams to make sure that you have a fair advantage. And the one actual very concrete thing that we want you to do in your report is we want you to build a system that will count the number of nouns in the articles. So we'll give you some test articles, but you can come up with some test articles and count the number of nouns in there. So that requires you to be able to find a way to get part of speech tags out of it. Okay, so that's what you have to do. We want a written description. We want your names and your Andrew IDs. I didn't quite say that. We have the French Andrew IDs. So give a French one with little accents on it. No, don't do that. Please give both, because sometimes it's a little confusing for us to remember your name, your official name, and your Andrew ID. So just make sure that you do all of that. Okay, so that's what I want you to do. This will be on the website by the end of today to remind you about that. But this is, not tomorrow, but now's the time to start planning to make sure that you know how to do that and listen to any of the lectures that may tell you how to do these things. So given that, I'll now pass you over to Adrian, okay?
Okay, so thank you, Professor Black, for the introduction. And as you said, my name is Adrian, and today I'm going to talk about hidden Markov models. So I believe last Tuesday, Dr. Martinson talks a bit about part of speech and how we can actually assign part of speech to a sentence using a very basic heuristic, which is to simply pick the most frequent tag. And we know that if we do this, then we will get the part of speech correct about 90% of the time. But I think one problem that we haven't really considered when we actually only take the most frequent tag for each word is that we do not really consider the context, because we only consider the word itself and not context. So how can we actually look at the context? For example, the preceding and the succeeding words, the preceding and succeeding tags. For example, if we have these prefixes like the, it's more likely that afterwards comes noun after the, and for to and transpose, it's also more likely to be followed by a noun, right? So that's kind of the basic kind of heuristic that you can use to actually assign part of speech. And so today we are going to talk about how we can do better rather than just assigning the most frequent part of speech. And for that we're going to use this running example, and we'll together throughout this lecture try to assign tags to this using So I guess this is a sentence, English sentence. Bill directed plays about English kings. So I guess to start, let's start with the kind of a small quiz. So for each of this word, there will be multiple possible parts of speech. So for example, the first word, it could be a proper noun, or it could be a verb, as in the company didn't bill me correctly, for example. Or it could be also a noun. Like for example, I requested for the bill from the restaurant. How about the second word? What are the possible parts of speech? Any answers? Plural? The idea plural? The directed.
It's verb, adjective.
Verb, adjective, yep. So adjective as in could be a directed graph or something. And for place, it could be a plural, it could also be a verb, right? And how about like the word about? What possible part of speech could this word take?
Preposition.
Sorry?
Preposition.
Preposition, right? That's one. What other possible part of speech? Adverb, right? And so usually about is used as an adverb, at least in country bank, when it's talking about like approximate numbers. So for example, the book cost about $3. So that in that context, at least in country bank, it's typed usually as an adverb. It could also be a particle. So particle as in it's part of a verb phrase, as in for example, bring about. So they make effort to bring about change. So in that context, about is the particle. And English as an adverb or adjective or noun, and kings as a plural noun or a verb as to make someone a king. So as today we're going to try to explore how we can actually find the most probable sequence of the archetypes. We start earlier with the basic heuristics, simply pick the most frequent one. So in practice, how do we actually start to find the most frequent part of speech for a word? How do we start? Like you're given a corpus, and how do you know like which part of speech is the most frequent for this word? Any guesses or?
Something really stupid is you can just count how many times each part of speech appears, and
Right. So,
even if it has multiple, just count all of them.
okay. Yeah. So they will give you a list of possible part of speech and their count. But it's assuming that we have. So of course we need to assume that we have a corpus where each word is annotated with the part of speech. So for example, you can use the pantry bank. I think it's also used in your homework research. And yeah, so we can list down the counts. For example, for Bill, we have maybe 41 counts as a proper noun, 2 counts as a verb, and 300 times as a noun. And similarly for directed, maybe in our purpose, it doesn't actually appear as an adjective. It only exclusively appears as a verb, but only appear 10 times. And similarly for place and about. So given the count, we can also actually calculate the probability. So in this case, we can calculate the probability of the tag itself given the word. So like this first table, the probability of having the word being assigned the part speech verb when it's the word bill, and it's about like 0.006. And similarly, we can calculate the probability of all words of the tags given each of the words simply by normalizing the count for each word. Okay, so we sum all the words here, 41 to 303, then normalize them, and we got the probability. So we can actually use this as a simple way to actually assign the most frequent one, because we can simply see which tag is actually the most probable. So similarly for English and things. Now, next, when we would like to actually incorporate context, this is where we consider hidden Markov models. So hidden Markov model is kind of a traditional model that's usually used, and usually part of speech tagging is the task used to exemplify hidden Markov models. And yeah, I'll briefly describe the formal description of hidden Markov models. So in this case, It formally it has what we call the start state and the final state, and also have the set of normal states. In our case, it will be the set of part speech, and we also have the vocabulary. In our case, it will be the dictionary of English words. And the last two parts are the major components for the Markov model, which is the transition probability gamma and the what we call the emission probability eta. So the last two will take a look in kind of more details in the subsequent slides. But the idea is that for the transition probability gamma, it's measuring how likely you are to transition from one part of speech to the next one. So for example, if you use the current word is tagged as a determiner, how likely it is to see the next part of speech being a noun or being a verb. So this matrix kind of encodes all the probability of that transition. For the last one, if the emission probability is kind of giving up the probability of how likely each part of speech gives or emits certain words. So it's the probability of the word given the part of speech. So we'll see later how these two parameters can actually be used to model the context, and hopefully you can do better in assigning part of speech rather than just simply assigning the most frequent one. So I believe Professor Alan Black showed this slide last week in classification. So hidden Markov model is another model that works as a noisy channel model that assumes a noisy channel model. So in this case, we are assuming that the generation process of a sentence or a sequence of words, call it, is that we start with some source that generates sequence of part of speech. So in this case, it's generated by gamma, because we know gamma measures or kind of shows how likely is part of speech to follow each other, and that can actually be used to calculate the probability of the sequence of part of speech tags. And then we goes into this noisy channel, and somehow part of speech get transmitted into a sequence of words. So at the end, what we see is the sequence of words, which is English speech, for example. And what we would like to get in part of speech tagging is how to get from the sequence of words into the sequence of part of speech. So that's what we call the decoding process. Right, so in the next part, I'll talk about how we can see this property of the part of speech tag sequence, or what we call the prior, using gamma. So we use the same example, bill-directed plays about English kings, and we have all the same candidate for the part of speech. So here we see three numbers. So these three numbers represent the first one, the probability of observing, or the probability of having a part of speech proper noun, given that the previous two part of speech are what we call the start state. So that's why we have the start state, and later we also have the final state. So given these, like the previous two part of speech are the start state, because we are in the first word, the probability is 0.2, for example, and the probability of having a verb as the first part of speech is maybe 0.02, and probability of having noun is 0.04. So this is kind of the probability of having these three tags as the first word. Then we can continue to the next word, because when we would like to calculate the probability of a sequence, we would like to measure the probability of, for example, having adjective following a proper noun, and having a verb following a proper noun, for example. So if we have, so this column here, the probability of adjective given start state and proper noun gives a number 0.004, and probability of verb given start state and proper noun, 0.129. So in this model, we actually we can simply multiply the probabilities of this with this one to actually get the probability of the sequence proper noun followed by adjective, and that using that, we get 0.0080081, right? So using this, we can actually score a sequence, like a whole sequence of part speech, simply by multiplying the probabilities at each position. So these probabilities encoded by this adjective, given, start, state, and proper noun, it's what encoded in the transition matrix gamma. So these are the numbers which are put into the transition matrix gamma. Then we can use that to actually score longer sentences. For example, this one is a sequence of 3 part speech tags, and yes, the probability gets smaller and smaller, but we see that some sequence of probability are more likely than others. But if we see here, actually, if we consider only the sequence based on the transition probability, it might not give the sequence of parts of speech that we want, because here the most likely part of speech sequence is that the third row, which is proper noun followed by a verb followed by another verb in this case. So that will translate to Bill as a proper noun, which is directed as a verb, but also place as a verb. But in this case, we would like to have place as a plural. So clearly having, like modeling the part of speech tagging using just the transition probability is not enough, because here we actually do not consider the word itself, right? So we need to actually include the word itself to get a better estimate of the picture. So that's what we do next for this part, which is the probability of x. X is the sequence of words given the tag sequence. So we can use the eta parameter to actually incorporate the information that maybe this part of speech is more likely to emit or to produce this word. Maybe a verb is more likely to produce a place than bill, for example. Then we can see some examples here. So in the beginning, we see that we, by counting for the tag for each word, and then we normalize per word, we get the probability of the tag given the word, right? But what we want here in the noisy channel model is that we would like to model the probability of the tag itself producing the word. So in other words, it's the probability of the word given the part of speech tag, right? So previously we see this equation. So it's the probability of the word given the tag, and then when later we can combine these two probabilities and multiplying them using base rule, we'll get the probability of the sequence of words combined with the sequence of our speech. Right, so for in this case, this one we have the probability of Bill given the tag proper noun. It's definitely much smaller, because now for each tag it needs to be able to produce all the words in the dictionary. And for example, the part of speech verb, it needs to be able to generate all possible verbs in the dictionary, right? So it's distributed over all verbs that is in the dictionary, and it happens that the verb bill gets a very small probability value, 0.00002, and similarly we can get all numbers. So here we see that when we sum over like the 3 pairs tags, proper noun, verb, and noun for bill, it doesn't sum to 1, because it's not probability according to the word, but it's according to the tag for our speech.
So, just want to confirm. So my understanding is for the first column, it's only the word bill, and there are 3 possibilities in that. I mean, you are like showing 3 possibilities, which is proper noun, verb, and noun. And for the second column, it's actually, for example, in the first row, proper noun, there are many words, and bill, the possibility of in that column, in that proper noun is only 0.000.
Yes.
Is this correct?
Yes, so technically, for example, we can draw a matrix where we have, in the rows, we have let's say we have 10 part speech tags, so we have proper noun, verb noun, adjective, particles, adverb, and stuff like that. And then let's say in the columns, we have different words in the dictionary. So For example, we have bill, directed, place, about, in the things, and all the words in between. So we can put for each cell in this matrix the count of certain word having certain part of speech. So that one we can do, right, using the simple method we simply count, right? And then when we say the probability of a certain type given bill, we are actually normalizing the counts over the column. So sum of the probability values over one column should sum to 1 if we normalize according to the word, right? But the second column is when we normalize according to the row. So like you said, for this row proper noun, there will be, say, I don't know, 100,000 words, and then we normalize over these 100,000 words, right? So this sum will sum to 1, but when we normalize according to the row, then we won't have sum to 1 in the column. Any other questions? So given the prior, which is the probability of the part of speech tag sequence, and the likelihood of observing the sequence of words given the specific parts of speech tags, we can actually combine them using Bayes' rule to actually get the probability of the part of speech given the sequence. So this final equation is actually what we want to measure, because at the end, what we are interested in is the sequence of part of speech. So we are given the sequence of words, which is X, right? And we would like to find out like which sequence of parts of speech is the most likely. So we need to find out the probability of the part of speech, given that we know what is the sequence of words, right? And using the Bayes rule, because we know already the probability of the part of speech tag sequence, which is the PY, and we also know using the matrix eta, what is the probability of the word given the part of speech tag sequence. We can actually calculate the probability of the most probable part of speech tag sequence. So this is kind of in the part of noisy channel model, which is also used in the HMM. Right, so the task itself, I think this is also defined by Dr. Martinson last Tuesday, that given a sequence of tokens or words X, we would like to find a most probable sequence of part of speech tags, one per word. So last time, I think we didn't consider a more complex model, this one, but now we can consider HMM, which is to find the most likely tag sequence. When we consider the basic heuristic, which is to find the most frequent part of speech tag for each word, and comparing to this HMM solution where we try to find the most likely tag sequence, the major difference is that for the basic heuristics, where we actually consider each word separately, we do not actually consider the interaction between part of speech labels, part of speech tags between adjacent words, right? While in HMM, we can actually take that into account. So we can actually model that it's more likely for a noun to follow after a determiners, and it's not likely to have a verb follows after a determiner, right? So this is definitely a more powerful model compared to our simple heuristics. And how can we do that? So yeah, in the next few slides, there will be a kind of formal and mathematical definition about the HMM method itself. We start with a sequence of states, right? So we assume that we have the sequence of our speech tags up until the first n-1 words, and we would like to find what is the most likely part of speech tag for this current word, given the previous n-1 part of speech tag that we have discovered. So because of the formulation of the HMM, where we consider only the last part of speech before the current word to actually get the probability of the current part of speech tag. So this is formulated using this formula. So in order to get the current part of speech, which is yn star, so star means the one that we already predicted or the one that we already had, it's the maximum part of speech which the part of speech that gives the maximum probability given the word sequence, and we also have the previous n-1 part of speech tags, right? And in this case, the second line V, it represents because we know that the probability of a part of the speech tag depends only on the previous one, but not, in this case, not maybe the previous 2 ones or the previous 3. So we only consider the one before it, which is the part of speech at n-1. So here V represents some sort of probability that the sequence up to n-1 words have the part of speech represented in yn-1 as the part of speech. So basically we have assigned until the word at position n-1 the sequence of part of speech, and this value represents the probability of ending at that part of speech. Given that value and given the likely that part of speech to be followed by another part of speech, the current part of speech, and how likely it is for our current candidate for part of speech to actually produce the word itself, we can multiply them together, and that's the probability that we would like to maximize when we would like to search for the best part of speech. Okay.
What is the F in the gamma IF?
Right, so here in this case, it's showing the equation for the last part of speech tag, and the F here is referring to the final state. So if you remember
okay. Right.
Yeah, this one, right? So we have the start state and the final state.
Right.
So yeah, later too we'll see some like walkthrough, like the simple walkthrough over the like step-by-step how we can actually or use some what we call the V algorithm to actually have the output.
Good.
Right. So yeah, this is part that I. So given like the n-1 for speech, we can actually have the like predict the next best one. And we can do this recursively, like, so starting from the beginning, we can do this recursively until the end, so that we can get the sequence of our speech for each of the words. So that's formulated formally using V algorithm. And here, we're considering the, it's shown as the recursive equations. So later, we'll also see some pseudocode to actually how do you actually write V algorithm. So for example, in the first one, we start with the start state, because all sentences start with the start state. The probability of starts at the start state is 1, right? So that's our base case. And then when we would like to continue predicting the next possible word, next possible part of speech, that we go through one by one. So for each time step P, and for each part of speech QJ, we find out what is the maximum one using dynamic programming. In this case, the V represents the best probability, the probability of the best sequence up until this point. Great. So at the end, our goal is to have the best sequence from the start state until the final state, transition into the final state. Any question up to this point? So that's the mathematical formulation. How do we actually code this to actually get the best sequence? So you can initialize all like the matrix V with all zeros, which represent it will be filled with the probability of the best sequence at this point, and we initialize the Q0 probability of start state at time step 0 with 1, and then we can gradually fill the table, the dynamic programming table, with the probability of the best sequence. And go through from time step 1 through n. Then for each time step, we need to consider for each part of speech at this current position, and we need to consider all the interactions between all the part of speech at the previous location. That's why we have the QJ and QI. QJ representing the current part of speech, QI representing the previous part of speech type. Right, so So for example, when we would like to run this algorithm on this sentence, we start with 1 at Q0 over there. And then we go through one by one. So the first time step, it's a bit misaligned. In the first time step, we fill this table because we go through the Q1 to, in this case we have four part speech. So we have the Q1 field based on its transition from Q0 and also based on the probability of Q1 producing build. So this is the, I guess because we do not have any options here, like from time step 0, there is only one way to go to time step 1 at Q1, which is this transition. Similarly, we can fill out the table for Q2, Q3, and Q4. And the next time step, we consider we want to fill out the Q1 for directed, which is how likely to have a sequence of part speech ending with Q1 at directed. So we will simply take the maximum of the scores from Q1, Q2, Q3, Q4 from the previous time step. Right. So this, when we do this using the formula shown before, we'll get actually the probability of the best sequence, right? So each cell at the end will be filled with the probability representing the best sequence from start state into this current state. Right. So using this algorithm, when it's trained quite well, and I guess you should be able to get easily around like 93-95% of accuracy. And next, what's interesting is that we should also look into what are errors made by the model. And this is from a paper in it's close to 20 years ago, but it's still relevant because you can actually see the errors made by the model. So for example, in this case, in this confusion matrix, the part speech tags in the rows represents the predicted part speech by the model, and the one at columns are the one the actual or correct part speech. So here we see the number 244 there represents like the errors where the correct part speech is actually GJ. GJ means here an adjective, where the model predicts it as a noun. So there, in some cases, there are some hard cases like this one is Navy officer. It's, I guess, even in country banks, sometimes they're inconsistent whether to assign this as an adjective or a noun.
One of the main reasons that there are errors like that in this data is the original data that they're training from is a Penn Tree Bank from 1992, and they didn't have conventions about how to do internal noun labeling for part and speech tags. So they're not consistent, which means that when you actually train an automatic model to try to do it, they make errors in the same way that the human made errors when they were doing it. So we can't just blame the model for this. We can blame the original labelers. I know some of them, but I'm not going to blame them or name them. John, you know who you are. So in other words, not just the model, there's actually genuine confusion in the data as well.
Right, yeah. So yeah, like that's a good point because part speech is, I think Dr. Mattenson should have talked about this a bit last Tuesday, that part of speech is not natural in the sense part of speech is not part of the language that we speak every day, right? So I guess I always remember this nice remark from Chris Dyer when he gave a colloquium talk, if you follow the colloquium talks here last year maybe. So he said that when babies actually learn language, they don't see Petri Bank, they see Wall Street Journal. It's like which means they see the text, but they don't actually see the part speech or the syntax. So because syntax or part speech are, we can say that it's a human construct, that knowledge that we actually put into like the language in order to understand language better. So yeah, that's why this kind of confusion happens, because most or sometimes people just don't agree on what should be the correct label for specific words. So part speech is not like inherent property of each word, but it's labels that you assign to them so that we can analyze them better, so that we can generalize systems, so that we can, for example, count nouns in an article like you're supposed to in your project and stuff like that, right? Yeah, another example is like confusion between particle RP and the preposition in. So in this case, it seems possible that could be a particle for like got around, or which means that the word around is kind of attached more to the verb got, or is it more attached to the noun phrase to corner? So it's a reasonable error speech right model, and yeah, this confusion between VBN, VBD and VBN, which is the VBD is the past tense and VBN is the I think past participle. So in this case, the sold is not past tense because oh sorry, this one is actually past tense. But if we actually replace they with the word the, then the part of speech for the sold actually changes from past tense into the past participle, because it no longer functions as a verb, but as a it's kind of some sort of adjective to the shares. The recently sold shares at numbers are yeah, these are some common models which are hard cases. So that's why I think part speech tagging is not a task that is like, I mean, people say that it's solved, because I think the best model for part speech tagging really reaches around like 98-99%, and I think in the past few years there have been I think the last paper like working on part speech was trying to find out what are the kind of the last remaining errors that we can actually look at to get to 100%. And yeah, the finding was that the 2% or 1% errors was mostly due to the confusion or due to the disagreement or inconsistencies in the annotation itself. So I guess that's why people say the part speech tagging task is actually solved. But yeah, here we will try to see like what is the progress between simply assigning the most frequent tag and using HMM to actually assign the best part speech tag sequence. So so far I think we consider when we create the tables of part speech and words, we do not consider the possibility of encountering new words, right? So when we see unknown words, how do we actually assign probabilities to them? Because we've never seen this word before, and for most frequent tag heuristic, we perhaps can do something by simply predicting the most frequent part speech tag across all words. That's, I guess, the best way we can do with the heuristics. With the HMM, we can actually do more compared to just considering the first of all, just the transition without considering the emission probability. But here, we can actually consider the properties of the word itself to be incorporated into the model. So for example, if we see a word starts with a capital letter, then human knows that it's more likely to be a named entity, right? It could be, first of all, a name for a person or a name of a location, right? And if it contains a number, it could probably be either adjective, as in like a 35-year-old man or something. And if it ends in ed or ing, then it's more likely to be verb, for example. So perhaps you have some other kind of ideas or what kind of features you can actually use for identifying the part of speech of the word. Other than considering the capital letters or numbers or end with ed, ing.
If it ends in ly, maybe it's an adverb.
As in ly, it might be an adverb. Yeah. Any other ideas? Okay, yeah. So I guess there could be. I guess in one of your homework, you're supposed to improve an existing bar speech tagger. Is that right? But yeah, might be you're not really expected to get like features, but you can. This is kind of one of the possible things that you can do actually. And yeah, so other features that you can use is prefixes as well. If it starts with an person, like could be an adjective, or interesting one could be word shapes. What we call the word shapes. So we consider not only that it contains a number, but maybe it's a number followed by a dash, followed by some sequence of letters, and it's perhaps likely to be adjective as well. Capitalization, lowercase, we see those examples before. Right, so so far when we talk about our speech, we seems to be assuming English, right? So here is the set of our speech from Country Bank. It's I think about 40, 41. And yeah, it's very fine-grained, but it's definitely not the most complex or simplest set of our speech, because in other languages there are many different number of part speech. For example, in Chinese, I think they define more than 290 part speech tags, and I think the smallest one you have 11. Yeah, like for Russian. So thankfully, you can actually use different numbers of part speech for different purposes, and I guess last Tuesday we see as well the Google, I think, open part speech tags. They provide like universal 10 universal speech tags, right? Like noun, verbs, adjective, adverbs, and yeah. So we can actually define the the sense of the level of granularity of the speech tag that you would like to use, and that depends actually on the task. If you would like, if for example, if you only need to find out nouns, you don't care whether they are plural or singular, then maybe you don't actually need the model to distinguish between them, and it will be easier for the model to actually predict this is a noun without confusing itself whether is this a plural noun or a singular noun or even a mass noun. Sometimes it's difficult to distinguish, right? Yeah, I guess in one example last Tuesday you have the Japanese. It could be a singular noun, it could be a plural noun, it could be an adjective as well, right? Right, so in other languages, when we have the data, so remember that the first step when we would like to estimate the most frequent tag or estimate the probability of tag a given word or word given tag, we need some legal data, right? So far in English we have lots of resources, thankfully, because of I think many years of work working for to build country bank, but it's might not be so in other languages. There are different challenges for different languages as well. For example, in English, it's perhaps kind of one of the least morphologically rich language. So in that sense, if we compare it to some other languages, for example, Turkish, I think they always like to use Turkish as an example of a morphologically rich language. But also some other languages like Indonesian. So that's my native language. They have, we have like lots of prefixes and suffixes representing different tense and different forms of the verb and also the nouns. So in that sense, it's kind of hard because if there are many word types, then it's kind of harder to define whether we should annotate the whole word as like one token, or we should split them into multiple words. For example, in in Japanese, actually they have, it's kind of hard, the issue of defining whether sequence of words or sequence of characters is actually a word or is that a combination of multiple words. So that's the issue that's present in other languages, which might not present if you work only on English. So here are some like challenges that if you work on other languages, what kind of challenges you may face. But yeah, so label data and the difference between English and other languages. So when we do not actually have the label data, either because we're working on languages for which we do not have label data, we can also try to get unsupervised pair tagging, which means we do not use the label data to get these statistics, but we try to induce or try to estimate or try to predict that this word might have the same like part speech tag as this word because they appear in similar contexts. Because if you notice when we assign part speech tag as in, for example, nouns or verbs, we're assigning them to like a specific class, and we make them consider the context of the word to assign different words into the same part speech tag. For example, noun always maybe appear after determiner, and all words that appears after determiner are classified into nouns, for example. So in this case, we can actually use the property of the language itself, the context, or how likely each word is to appear in certain contexts to actually assign them with part speech tags. So for example, we have, we consider the context W1 and W2, and we consider all words X that appears in this context. Context means this word appears when the previous word is W1 and the following word is W2. So we can similarly like count the list of words and the most common words and all words that appears in this context. We can give them the same part speech tag. We can do this, for example, in English, do this 10 times, and we get like different words classified into the same categories. For example, Mr. and Mrs. are often classified together, and for example, she, he, it, and you are often appears in the same context, so they appear in the same cluster, or we give them the same class, the same part speech tag, right? But we do not actually have like semantic meaning to these clusters unless we actually look at the words inside and give some labels to it. So there are some methods to actually do supervised pair tagging. One of them is the old method, Brown clustering. So this is a method to actually cluster words based on the mutual information between the words. And I think there's a paper that describes the actual method to like the description of Brown clustering. But I guess nowadays when people say that they use Brown clustering, what they mean is that we use code from Percy Liang, who wrote the code from I think 2005, and just run the code on this corpus, and they got the clustering based maybe 1,000 clusters, and then use them to as features of their model. So yeah, it's again like all unsupervised pair tagging. It's not semantically meaningful in itself. Like we do not have inherent labels to each cluster, but we can actually see the correlation between words because they appear in the same context. For example, we have an example here of a database of flight information. If we often see to Shanghai, to Beijing, or to London, then maybe we might assign these words to the same class, for example, class 13. It might represent something meaningful, or it might not be. But hopefully, using this clustering method, it might give us meaningful clusters so that we can use them as features for our downstream models. So the idea for Brown clustering is that, in summary, it's a hierarchical clustering method, which means first they pick greedily the two most words with most similar context, and then combine them into one cluster, and then we perform this repeatedly. find another pairs of words which are more similar in context and then put them in the same cluster. And we do this until all words are put together into one cluster. And then we can simply like pick some levels in the tree to actually use them as our set of our speech tags. Right. Yeah, so these are some methods to actually do unsupervised parse speech tagging when we do not have enough data. So I guess in summary for parse speech and tagging, the idea, I think Dr. Martinson mentioned this last Tuesday as well. It's a tag that represents the correlation between words. And we have some rules class which are parse speech tags which might not like be open to like new words like determiners or pronouns. We only have a limited set of pronouns. You don't usually invent new determiners for English, for example. But for other open class like nouns, verbs, adjectives, like adverbs, people do invent like new nouns or new verbs, right, all the time. And then today we discussed about how we can use HMM or hidden Markov model to actually get the best prediction or get the best sequence of parse speech tag given the observed sequence of words, in this case the PX or keyword. So we simply use the keyword given tag, which is the emission probability multiplied by the prior, which is the we use the transition probability here. We discussed a bit about HMM and how we can use bigger-B decoding to actually get the exact sequence using the recursive formula and probably using the pseudocode. And we discussed also about unsupervised tagging, and one of them is ground clustering. So there are many methods to actually, you can actually use ground clustering in English to get some unsupervised parse speech tag. Perhaps for your domain, you need more fine-grained parse speech tag than what Countryman offers. Then you can use unsupervised tagging for English to get your parse speech tags. So which method to use for your task, it depends on like how well it works for your task. And for example, for the ground clustering, you can actually define how many clusters you would like to use, and that is actually some hyperparameters that you can like tune. For example, if you would like to find out like which number of clusters actually works best for your model. So I guess that works mostly for non-neural models. So I guess recently with more neural network models, we don't see this as often, but sometimes people do include some handcrafted features like the next parse speech or the current parse speech or the current unsupervised ground clustering, for example. So these are the use cases for these parse speech tagging. And yeah, you simply like try several alternatives and find out which one is best for your task. So I guess we still have some time. If you have any questions, yeah.
So if you do clustering initially for some certain number of rounds, would it then help to make an HMM based off of the clusters you have in order to get better classes for the remaining words, potentially?
So, yeah, I guess for that one, so you're saying that we start with the unsupervised clustering,
right,
to get some sort of like initial labeling,
right,
and then we can propagate that. Yeah, that's a good idea. And I think you can also, on top of that, you can actually use partial information as well.
Mm-hmm.
For example, you know for certain that this word has this parse speech tag, but you do not know the rest of the words. You can also use HMM on top of that. But when we do actually this thing,
mm-hmm,
when we measure the probability, for example, if you know that directed is definitely a verb, then you simply put the
right,
probability as 1 and the rest as 0.
right,
Right? And then you still do fill up the rest of the table as pronoun. Then that's kind of part of how you can actually use partial information or excellent information. That's good.
Yeah, the same size. So why does the video has process?
Oh, so for this case, because like in the code itself, it's usually easier if we consider all possible speech tags for all words, so that we can simply make a like n by n table, right? So if you do not, for example, if you do not want certain words to be assigned like certain labels, you can actually hard code that to be 0. For example, if you can assign this to be 0 and simply run the algorithm to all other cells other than this specific cell, for example.
So one of them, the probability of one of them is zero.
Sorry, again?
I mean, one of the probability is zero.
Yeah, if you, for example, for and in the example, I think we have like 3 possible points, right? Pronoun, what else? Noun and verb, right? If we want, we can actually put one of them as 0. Like maybe we do not want this to be assigned as determiner. Definitely, this is not a determiner, right? Because we know all the list of determiners. Right? But for open class, usually we would not like to be that strict because sometimes we do not see the use of certain part of speech for a certain word. For example, in our example, I think directed only appears as verb or maybe plays, right? So it appears 10 times as a verb, but not as an adjective, right? But it's actually possible, right? But it just does not appear in our corpus. So when we actually count the occurrences of our speech tag and the words, and we find that it's 0, it doesn't mean that it will never occur in the data. It might just be that our corpus is too small, or maybe it just doesn't appear in our domain. But it's still possible to appear in some case. In that sense, we still give some probability to that tag. So that's why we do not hardcode it to 0. Yeah. I guess this kind of smoothing is one of the methods that you can try for your work papers. Any other questions?
So when you calculate the probability, do you calculate the probability of the whole sentence or only like the probability of the 2 words adjustment together? So if like your formula is calculating BO directed, so you say, okay, what's the maximum probability of BO being noun and direct being verb?
Right.
Or you calculate BO directed like the whole sentence, what's the highest probability of each word like being some out of speech?
Okay. So for HMM model, when we actually do the variability coding, it's actually trying to get the best possible sequence over the whole segments, right? But at any point in time, for example, at this point here, it's measuring the best probability of assigning PS tags to field directed. And for example, this cell will measure the highest probability of field directed place, ending with this Q3 assigned to place. Right. So I think in one sense, you do measure like the highest probability in like up to a certain point, but because you want the whole sequence to be, you want to find the best sequence for the whole words, like the whole sentence. So you keep doing this until the end, and at the end, you will get the best sequence of all overall possible sequences. Does that answer your question?
For the unsupervised tagging, I might have missed this, but what are we repeating when it's on the slide?
Oh yeah, it is English, right? Yeah. So for example, you consider like different contexts, and when you assign them to the same cluster, you get the cluster for certain word, right? And then I think for this one, it's not simply just repeating the context, but also trying to see. It's I guess also using the count itself. So for example, using the first run of this clustering, you count how many times this word is assigned to this specific class, for example. And then afterwards, you can use this information that this word is more likely to be assigned this class to when you repeat the next iteration. There are many ways to actually do unsupervised PR tagging. So this is just kind of one simple way. Any other questions?
So what's the purpose of using like this method? Like, okay, we are trying to understand each word, what's like, if it's a noun, if it's a word, the whole sentence, the whole document.
Right.
And what we are going to do with that? Like, what's the purpose of using that? What's the next step?
So you mean the task part of speech tagging itself in general?
Yeah, like after you have the part of speech finished, what are you going to do with it? Like, what's the purpose? I still don't understand that whole.
Oh yeah. So basically, the simplest one will be to filter. For example, if you would like to make a model for recognizing name entities, right? You can start with consider all possible nouns, and then you classify only those nouns, right? So that could be an easier problem instead of consider maybe just simply take all possible like sequence of words, because for example a simple model for recognizing name entities will be to find words starting with capital letters, right? Because those are more likely to be name entities. But if we found out that after running PS tags that maybe this word starting with capital letters is actually part of maybe it is a headline, right? But our part speech tagger actually knows that this is a headline, and the sequence of all entities is unlikely. It's more likely to be a noun followed by a verb, followed by another like noun, for example. Then it's a useful filter for the next step for the name entity recognizer. Yeah, that's kind of one application.
Or maybe it's useful like for the homework coaches that are going to ask questions, like leave questions out of the documents, right? So
Yeah.
we need to understand what are
Yeah, which ones are possible answers? Yeah. So I'll talk a bit about HMM and other logistic models. So this is kind of a summary of, I think, maybe not necessarily, but we talked a bit, I think last week, Professor Andre talked a bit about the APS classifier, right? I guess. Yeah. And HMM is similar to naive-Bayes classifier in that it's what we call the generative model, because first we model the probability of the sequence given the of the words given the our speech tag. Similarly to in naive-Bayes, we model the, I think in classification we model the probability of the article given the class, for example, sports, right? And naive-Bayes is a single class and HMM is a sequence. If we move from joint or from generative model to another type of models called discriminative, we get another set of models, which we call the discriminative models. And some of examples of them are maximum entropy, which is similar to naive-Bayes but it's conditional, and the more famous one is conditional random fields, or CRF. So this CRF model is actually still used today. So HMM might not be used as often today, but CRF is still being used often, even in the era of neural network. And that's a kind of still a useful method to model to know actually. And yeah, I guess I put this here because my research previously before I came here mostly deals with conditional random fields as well, and we're trying to kind of consider different structures of the model itself. For example, I think one question just now: what if we know that certain words do not cannot possibly be assigned certain chaos tags? How can we actually modify the table or modify the links between the cells in the table? So we actually export that, and there are actually many variants of how to do this kind of what we call the structure prediction on sequence. So the standard one is the linear CRF, or it's very similar to the HMM, but just different formulation. Instead of modeling probability of the word given the tag, we model the probability of the tag given word directly using features. But there are also other variants like what we call the semi-Markov. So one word, maybe the third word could depend directly on the first word. So if the first word has this tag, then it's more likely for the third word to have another tag. We saw some examples just now, like when we see they recently sold shares at, and if we change the first word into the recently sold shares, then it changes actually the third word, but not the second one, right? So we can model that using that one, and yeah, I guess I would like to include this because it's kind of interesting anecdote of my own research. Like, I proposed this model by accident because I was initially trying to. So this was kind of my first paper. So my first paper in 2016. So initially I was trying to understand how a semi-Markov model works, right? And I was implementing it, and as I showed it to my supervisor, then as we discussed, that it became clear that what I implemented is not correct, and what if I implemented is not actually a Markov model. But when we look deeper into what I implemented, actually it's something that's still useful and still new, and we simply propose it to submit to the conference. And yeah, because it's new, and we have, I think, another data set to be like that comes with this one, so that becomes kind of my first paper. So it's kind of funny that my first paper is actually by accident, but it's kind of encouraging in the sense that if you would like to do research later, you don't have to be discouraged if you kind of maybe misimplemented something, because it could be something new. Yeah, and yeah, I guess there are some other barriers like dependency guided, like you limit the power speed stacks, for example, by another structure, in this case by dependency parsing. And you can also have a more complex one, like in this case we use hypergraph model to actually so this is still some sort of sequence like HMM, but it's more complex in the sense like one node can be connected to multiple nodes. And this one was used to model discontiguous entities. Like in this case, I think FEOP speaker capture is, first speaker capture is one entity. It's kind of separated multiple words. So yeah, I guess that's all I